You asked the AI to write a function, it did. The code looked clean. The variable names were sensible, the logic tracked. You ran it, it passed. You shipped it. 3 days later, production went down. And the strangest part is not that the code failed. The strangest part is that it was never wrong in any way you could easily see. It was confident, it was coherent. It was broken in a way that only becomes visible at scale, under real conditions, with real data, in a real environment that no AI ever touched. That is the problem nobody is warning you about loudly enough. Everyone is talking about whether AI can write code. That question is already answered. It can. The harder question, the one your team will spend the next decade wrestling with, is, can you trust what it wrote? Trust is not the same as correctness. A function can be syntactically correct, logically structured, and completely wrong for your system. A test suite can be green and still miss the failure mode that takes you down at 2 a.m. A diff can look clean in review and carry a subtle assumption that was never true in your specific environment. This gap between apparent correctness and actual reliability is not new. It predates AI by decades. In 1962, NASA lost the Mariner 1 spacecraft due to a single missing hyphen in a guidance formula. The code passed its checks. The rocket still veered off course and had to be destroyed. In 1996, the Ariane 5 rocket exploded 37 seconds after launch because a 64-bit floating point number was converted to a 16-bit signed integer. Code that had worked perfectly in a previous rocket with a different velocity range. Correct in context A. Catastrophic in context B. Now multiply that problem by a system that generates thousands of lines of code faster than any human team can review them. The research backs this up with uncomfortable precision. A 2023 study published by researchers at Stanford and NYU, often called the GitHub Copilot Security Study, found that developers who used AI coding assistants were significantly more likely to introduce security vulnerabilities than those who did not. Not because the AI wrote obviously bad code, but because the AI wrote code that looked trustworthy. The researchers identified something they called automation bias. When a system presents a confident, well-structured output, humans reduce their critical scrutiny. The code looks right, so you trust it. And trusting it is exactly when you stop checking it. Automation bias is not a weakness unique to junior developers. It is a documented cognitive pattern that affects experienced engineers, pilots, surgeons, and financial analysts. The more polished the output, the more the human brain discounts the need to verify. AI coding assistants are extremely good at generating polished output. This is where the real danger lives. Not in the hallucination that invents a function that does not exist. Not in the obvious error that any linter will catch. The real danger is in the confident, clean, structurally correct code that solves a slightly different problem than the one you actually have. Think about what that means for your codebase right now. Your AI assistant does not know your database schema the way your senior engineer knows it after 3 years of working with edge cases. It does not know that one table has a soft delete flag that behaves inconsistently across 3 legacy migrations. It does not know that your authentication service has a known race condition under high concurrency that your team documented in a Confluence page nobody has read since 2021. It does not know that your staging environment is missing a third-party service dependency that only breaks in production. The AI knows what you gave it. It knows the context window you opened. It knows the function signature, the surrounding file, maybe the files you pinned. It does not know what you did not tell it. And what you did not tell it is often exactly what matters. This is what researchers at DeepMind and Google Brain have started calling the context gap. In a 2024 paper examining the reliability of large language model outputs in production software environments, the authors found that the single strongest predictor of AI-assisted code failure was not model size, not temperature setting, not prompt length. It was the mismatch between the context the model received and the actual operational context of the system where the code would run. A model given perfect context produced near-perfect code. A model given incomplete context produced code that was confidently, plausibly, wrongly calibrated to the system it was supposed to serve. You are probably already feeling this. You have had the experience of asking an AI for a solution, getting something that worked in your test environment, and later discovering a hidden assumption baked into the generated code that your environment never met. That assumption was not random. The AI was not hallucinating. It was filling in the context it was not given with the most statistically likely behavior from its training data. Which is another way of saying, it built code for a generic version of your system, not your actual system. The question this raises for your team is uncomfortable. How do you evaluate the output of a system that is almost always right in ways that are hard to verify, and occasionally wrong in ways that are even harder to detect? The answer emerging from the most serious engineering organizations is a discipline called evaluation engineering, or evals. Google, Anthropic, and several large financial institutions with AI-integrated codebases have started treating evals not as a testing afterthought, but as a first-class engineering artifact. An eval is not just a unit test. It is a structured proof that the behavior of the system matches the intended behavior across a defined distribution of inputs, including adversarial inputs, boundary conditions, and the specific failure modes most likely to matter in production. The difference between a test and an eval is the difference between checking that a bridge holds under normal load and checking that it holds when the temperature drops, the traffic doubles, a truck exceeds weight limits, and the bolts have been in place for 20 years. Tests verify the expected case. Evals probe the edge of confidence. Martin Fowler, in his work on continuous delivery and software reliability, has long argued that the cost of defects is not linear. A bug caught in development costs 1 unit of work to fix. A bug caught in staging costs 10. A bug caught in production costs 100, and that number does not include the reputational or security damage. That cost curve has not changed. What has changed is the rate at which code is being generated, reviewed, and shipped. If the generation speed increases tenfold and the evaluation rigor stays constant, you have not made your team 10 times more productive. You have made it 10 times faster at shipping unverified assumptions. This is the counterintuitive truth that experienced software engineers are beginning to accept. The bottleneck in AI-assisted software development is not writing code. It has not been writing code for some time. The bottleneck is now verification. Knowing what you have. Knowing where it will break. Knowing what you cannot see yet. And here is where it gets genuinely strange. The same AI systems generating code can also help you build the evals that catch their own failures. Anthropic's internal engineering teams have reported using Claude to generate adversarial test cases for AI-generated code, using one part of the system to probe the weaknesses of another. This is not a comfortable idea. It is also not optional. When the volume of generated code exceeds human review capacity, the only scalable option is augmented verification, not less verification. Your job as a software engineer is quietly changing shape. The engineer who will be most valuable in 5 years is not the one who can generate code the fastest. It is the one who can look at a generated diff and identify precisely and quickly where the hidden assumptions are, where the context gap opened, where the AI built a solution for a system that does not quite match yours. That is a skill that takes experience, domain knowledge, and a disciplined habit of distrust that the confidence of AI outputs will constantly work against. You asked the AI to write a function. It did. Now comes the hard part. Proving, not hoping, that it works. Not in the demo. In production, in your system, with your data, under conditions the AI never saw. That is the skill the next era of software engineering is actually going to demand from you.